Hello everyone, I'm Associate Professor Ömer Melih Gül from Istanbul Technical University, and today I would like to talk first AI/ML based security, the RF fingerprinting type of security for the some ground transmitters, device or UAVs and some aerial communication. And then I will continue with some AI/ML based approach for the maritime security and IoT data spoofing in some manner. So it seems I have two presentations, but when you consider the close relation between some problem, then you will see the connection will come automatically. Then we can have some discussion, and I will be happy to discuss on that. Okay. As I said, I am Associate Professor at Istanbul Technical University, and when you consider my research interest, it is generally based on some computer communication network, but I also have some AI/ML applications and also some AI/ML based security and a bit blockchain, and also I have some robotic and control background. So I also interest with UAV and also multi-robot systems. So we can extend the research work in that manner. And today, as I said, we will start with some AI/ML based security solution for the classical RF communication on the ground and also in the aerial communication, but then we will continue with the maritime. We start with the fine-grained augmentation for RF fingerprinting under the impaired channels. When you say impaired, we consider that it is not a perfect channel. We will talk about some different type of AI/ML based approach. So let's jump that. Okay. First, we will give some motivation why we consider RF fingerprinting. Okay, for example, we talk about fine-grained data augmentation. The data augmentation is a well-known approach in AI and ML, and we talk about some kind of RF fingerprinting. What is RF fingerprinting? And when you consider impaired channel. So first, we will give some motivation of the problem. Then we will give some closely related literature. Then we will talk more on system model and problem definition and give some more background and dataset introduction, because we are talking about AI and ML. So we need to give some, we need to introduce the dataset, because the dataset will change, the results depend on also the dataset. Some datasets may be more challenging, some datasets may be easy. So it will affect the results of the proposed approach. The proposed approach based on data augmentation, we will introduce that and then give some numerical result and conclude, and also future work. When we say the proposed approach based on data augmentation and numerical result, here we also include the sensitivity analysis. Okay, we are engineers, right? So as engineer, we propose some solution. It is well, and we want this solution to work well, but we also consider our solution to be resilient depending on the change. So when we say sensitive to analyze, our aim is not to have a sensitive system. Our aim is as much as non-sensitive or insensitive system, to obtain insensitive system. So we when we achieve a good result, depending on the parameter change, we don't want it to change. We want it to not change, or if it is change, then change slightly. So sensitivity analysis is also important to show the strength of our proposed approach. Then we will conclude and give the future work. In fact, when we say future work, the future work is also given in the second part of the presentation. Future work is more on IoT data spoofing. Okay, we are talking about the motivation. What is the motivation for dealing with such a problem? We have some autonomous vehicles. They are prone to some spoofing attacks. Okay, people try to, you already know that the spoofing attack, you try to mislead the identity, and you try to sometimes imitate, you try to imitate the autonomous vehicles or some other device, or you try to mislead. Okay, you want people to not to understand the exact position or identity. So of course, autonomous vehicles, especially when you consider UAVs, which are really expensive device, they are prone to spoofing attacks. And we say that, okay, when you consider the security, we can propose some networking security approach. But when you consider cryptographic approach, or maybe network layer security, they may be complicated, or maybe you need some other communication, something. But they say that, okay, instead of that, can we propose a kind of security by design approach? For example, can we consider the security just come from the design of the system? So the wireless device have some malfunctions due to production. Even if you take some kind of circuit theory or analog electronics lab, something, you know that even the simplest electronic component, you know the resistors, not in even resistors, something. If you say, for example, if it is 1 kilo ohm, it is generally not 1 kilo ohm. It is 1003 ohm, or 1005 ohm, something. So even the small components have some difference because of the some malfunctions, difference because of the production, right? So when you consider this type of small production, when you create some large products or circuits, anything, then their effect may be much more than the input. Sometimes people say butterfly effect. Yeah, even it may be something like that, butterfly effect. Okay, just maybe there is a, 0.2% difference, but it may cause 20% difference in the output. So we say that, okay, can we consider, can we benefit from this difference? Everyone has their own fingerprint, and they say that, okay, because of this production, can we obtain some kind of difference between two devices? And they say that, how we can observe that? They say, okay, their effect can be seen in RF frequency waves. When you consider the RF waves, what they send some kind of signals, right? And if there are some difference in the input, even the input signals are same, but if there is some difference between these two devices, then the output may be visible. That is the approach. That is the motivation for this security by design approach. Every device has their own effect, RF fingerprint, and they show their unique behavior. This unique characteristic is called RF fingerprint of the device. So you aim to send the same message, maybe 1001, but the output is not same. Output may be different, maybe slight difference, but still there is difference. And when you consider URLC, it is ultra reliable and low latency communication. It is one of the three core features of the 5G, whereby 1 millisecond latency is aimed. So we want some resilient solution, and we want some practical solution, fast solution, instead of always computational expensive solution. We want some practical solution. So we propose RF fingerprinting based approach, which provides some kind of physical layer security, which is more practical solution than the network layer solutions. And here, Okay, we talk about RF fingerprinting, but when you consider the difference between these two signals, how you classify, how you understand, okay, there is some difference, but how you understand, how you give some kind of meaningful uh, weight, okay, how you say, okay, there is some difference, but what will you infer? In such case, we apply some AI ML-based approach. You know that why people propose this type of approach. If everything is clear, if the function is clear, you generally propose optimization techniques, right? Because function is okay and you will try to optimize the function, minimize the cost, maximize the reward. That is the optimization, right? But this type of problems is not optimization problem. This type of problem is a kind of black box. So you try to understand the approach. So you try to use AI ML based approach where the machine learning analyze the historical data, identify the patterns of those signals, and provide some insights for future predictions. Here it says the ML, in fact, it considers even the supervised learning. So here we try to learn the RF fingerprinting with machine learning. We train our system, and when the new data come, we will say, okay, this transmitter try to imitate the others, but I know you, I know your identity, not try to imitate the other. So that is the approach of AI ML based RF fingerprinting approach for our security. And when you consider some brief literature, the RF fingerprinting methods are compared by considering the four features. We consider demodulated or real data. Here we consider the real data and also different data. For example, here we train our system with the RF fingerprints samples of day one, and then we test our system with the following day sample. For example, today we train, and if we test again today, then okay, we will most probably obtain some good results because why? At the same day. But even tomorrow, when you test the system, then the problem is more challenging, but still we consider that. Also, we consider multiple waveforms. What are the waveforms here? In fact, to find a correct name may be difficult, but in fact, we consider multiple communication systems. Like 5G is another protocol, right? Another generation, another approach. 4G is another one. And when you consider Wi-Fi, it is another one. Even those transmitter device use different protocols, different approach systems, different generations. Then still we try to understand, we try to identify each transmitter. And also we consider some CDL and TDL type of augmentation analysis. We talk this one. In fact, when you consider our approach here, as I said, we propose a fine-grained augmentation. We will say that how we make the augmentation. Okay, when you consider the brief literature, in the brief literature, that is the brief literature for our previous techniques. Let me say, in the literature, they consider real data and also different data, but generally not multiple waveforms. Some of them consider multiple waveform, most of them not. And here we consider different type of augmentation. If you deal with machine learning, you know that augmentation. If you don't have sufficient data, what you are doing, you try to increase the amount of data, right? But how you will increase, how you will augment that data? Then, okay, you can use the same transform for all data, maybe add some noise, or maybe use the same transform. But here we say that, okay, instead of transforming all data with the same one, what about transforming different class with different class with different transformation? For example, in our problem here, we have 3 class. How we can augment them? We say that, okay, let's make some class specific augmentation. Because if you make the same transform for all class, it may change the data structure in unmeaningful manner. So after considering the classical augmentation, we say that, okay, let's at least augment some class with CDL and TDL type of transform. This transform generally used for 5G, but we apply CDL transformation for 5G data and the other transformation for TDL. We will talk a bit more. And now, after our approach, that is a middle step. With this approach, we publish a conference paper. We had 3 conference papers from this topic and 1 journal paper, in fact 2 journal papers. And this approach received the best paper award in the various World Research Forum. We can talk a bit more later. Okay, then we consider the problem in more general manner. We say that, okay, in the literature, they consider again demodulated data or different data or heterogeneous waveform, multiple waveform anyway. But in this work, we consider fine-grained augmentation. In this work, our most recent work on this RF fingerprinting, we propose fine-grained augmentation. It means that each class of the data augmented with different transformation. I will directly give the flow diagram of that approach. Okay, we give some motivation, we give some introduction, then we give some related work, and let's talk about the system model and problem definition with this figure. Okay, for example, in this scenario, we may have a different device, some access point or transmitters, or even some UAV, some device. And also, they try to communicate with these, for example, mobile phone or some other device. And here, two transmitter try to communicate with this mobile phone, and also the base station of Wi-Fi, for example, the Wi-Fi device. It also try to communicate with this mobile phone. So here the base station 4 and 2 communicates with the mobile phone, but they may try to resemble base station 1 and base station 2. For example, these guys may send some malicious signal or some different type of signal or some other problem. Some people may use this base station, this transmitter, but they try to, mislead the recipient guy, and that guy may say that, okay, the problem may come from this base station 1 or base station 3 something. So in this type of problem, what we say, that is a kind of spoofing attack, right? So in this type of attack, we try to avoid this type of misleading, and we will say that, okay, I know RF fingerprinting of each of you, so you are sending the signal. I know base station 2, you are sending the signal. Or when the base station 4 sending the signal, I will say, okay, base station 4, you are sending the signal. I know you. So we try to avoid these misleading. But as I said, we try to make the problem a bit challenging. We try to train the data. What are data? The data are RF samples uh, received by those transmitters. We have some train data, and we use this training data to learn their RF fingerprint, make inference about RF fingerprinting, and then in the following day, when the signal come, we say that, okay, I know each of your identity. And we investigate the data for channel impairments and environmental changes like temperature. So by observing those RF fingerprints, those RF signals, we try to infer some RF fingerprinting, and we try to understand the channel impairment. What are the channel impairment? The channel impairment are the effect of those transmitters, each transmitters on the signal. Think about all the transmitter may be identical in the idealistic world, and then the same signal will be sent as the same signal by all transmitters, right? But instead of that, each transmitter has their own fingerprint, so they make their own channel impairment. And we work with data sets composed of 3 different communication technologies, waveforms, anyway, heterogeneous waveform, 5G, Wi-Fi, and LTE. LTE is called as 4G. And we use the powder data set, which is collected by some guys from Northeastern in Boston. This powder dataset is presented by Chaudhry's group at Northeastern University in 2020, and here we use 45 sample files for each of day 1 and day 2. So we have 45 sample files day 1, and then we have 45 samples for day 2 as the test data. And thinking about that, we have 3 waveforms, 5G, LTE, Wi-Fi, and 3 transmitters. They call as BES, MAP, and Browning, and then 5 samples from each transmitter for each waveform. So we have 45 sample files for each day 1 and day 2. And we assume that we have only one antenna at the receiver side and just one IQ values provided by powder dataset. We consider this only one antenna at the receiver side because when you consider multi-antenna, then there will be interference. The problem may be more complicated. It may be considered some kind of future work. And then when you consider one IQ value, it is provided by powder dataset like SISO, single input, single output. So these are some information for for this technique. Sorry. Okay, we propose 2 different augmentation techniques. The first one is tap delay line, TDL, and cluster delay line transformation. This transformation are the 5G type of transformation, and MATLAB has very good resembling or imitation of this transformation. And this approach, this problem is worked under a project collaborated with industry in Canada, and even the industrial companies say that, okay, really the CDL, TDL models in the MATLAB is too realistic. You know, there is even no difference between the real world and also the MATLAB environment. So we say that, okay, let's use this type of transformation and transform the data. Thus, we can augment the data. We keep the original data, but also we transform and make a second copy. Let's say, not second copy, a modified copy, modified version. Thus, we doubled the sample. Instead of 45, now we have 90 sample for day 1 and 90 sample for day 2. And then we consider class-specific fine-grained augmentation. The TDL-CDL transformation, here we have tap delay line and cluster delay line. So here they are similar to each other. CDL is a generalization of TDL, and they have some correlation. It is proposed in our previous work, one of previous work in ACM YSML in 2021. That is our first paper, conference paper on this topic. It is on ACM Wireless Security with ML workshop in 2022, and we use MATLAB generated channel profiles with that, and then we add to day 1 data. And when you add it to day 1 data, then the day 1 data become 90 sample. But sorry about that, we didn't make this augmentation for the day 2. Why? Because we use day 2 as test data, and we don't want to make the test data more and more challenging or augment the test data. We try to augment train data. And we have some separate mean files generated by using MATLAB functions, CDL, TDL, and the model is trained just on day 1 and test on day 2 to deal with impairments. We consider TDL augmentation, CDL, TDL plus some noise, and also CDL plus some noise. These are some approach, some middle steps on the way of the fine-grained augmentation. And we increase the performance just 3% when you consider the approach, the machine learning-based approach with no augmentation. Okay, in the machine learning, generally when you consider deep learning, you use some CNN. Okay, you use some CNN, but the CNN doesn't have sufficient performance. It achieves 75%. In that case, what you will do? You will use some CDL and TDL. And okay, we talk all this approach in verbally, but okay, professor, you are talking about all these, but what is the flow diagram? Okay, that is the approach, that is the CDL, the decoupled CDL, TDL data augmentation. We have data samples, we have data split. In fact, that is already known. That is trained data, day 1. That is test data, day 2. And we know that we know the train data, which of them are 5G, which of them are 4G, which of them are Wi-Fi. So we separate them, then we augment all, but with different transform. For 5G with CDL, for Wi-Fi with TDL, for 4G, nothing. And we augment the train data, then we have a classifier approach, and then we use test data to test the process and test the output. So you may say, is it okay? You can separate train and test data, but is it easy to separate 5G, 4G, or Wi-Fi? Yeah, why not? Think about it. They use different generation. Even their approach, their protocol, they are very, very obvious. They may use different headers or different length of headers. If you take some network course, you may see the difference. You may see the update. Think about the 5G and 4G. There is 1 decade difference. between these two one. And so you can even investigate the 4G core network, 5G core network, and you will see there are really much difference. So it is not a big deal to understand which data is 5G, which of them is 4G, which of them are Wi-Fi. So we can apply the separate transformation. And here we keep the 5G, but also we have 5G CDL. We keep Wi-Fi, but also have Wi-Fi TDL. As I said, that is a middle step. And also we, after making augmentation, now again we have the VGG type of classifier. Here, VGG is generally some used convolution neural network infrastructure, some framework which help us to classify the data. Sorry. Okay. Okay. We talk all this, right? After all this, if we talk about the accuracy, then if we consider the accuracy on day one, generally it is above 95%, 97%. Why? It is because it is like that. You train the day one, and again, if there is a day one data, then you understand, you predict everything accurately, almost perfect accuracy, you predict everything. But when you consider day two, without augmentation, just by using CNN-based approach, you will achieve 75%. But if you consider CDL, TDL-based augmentation, it is 78, but CDL plus TDL augmentation, the last one, it is about 88%. That is 88%. Okay, we talk about data, right? So instead of just talking about these numbers, it is also better to give some TSNA. If your data is very complicated or some long samples, think about each sample. Here, each sample may have 3 million instances or nearly 5.3 million instance. Okay, 5.3 million points, dots in each sample. So it is a long one. So in that case, we use TSNA. If it is short, then maybe we could use PCA, principal component analysis. But if it is a large one, then we use stochastic neighborhood approach. With this approach, we reduce the dimension of the data. For example, this data may have many dimensions because it may have many features. We reduce dimension of data to the 2-dimension, and thus we can visualize it better. Okay, instead of try to represent the data with large dimension, we try to represent in 2-dimension each data, each point. Normally it may be, for example, this point normally may be 1, 2, 3, 4, 5, 6, or 1 million, blah, blah, blah. But we make it as, for example, 3, comma 5, just with 2 points. Okay, that is a 1 coordinate, right? 2.1 coordinate. Let's say it is x1, y1, just 2 coordinates. By making this, you can observe, for example, for base station 1, okay, the base station 1 is this, and the base station 2, that is the second class. The base station 3 is this one, and that is the base station 4. So here we have 4 class, but we also talk 3 class. And here we see that, okay, this class is a bit problematic class, not a normal class like that. So we consider this class, we use this class later. We remove this class and just work with base station 2, 3, and 4. And then we will use this class to make some interference and noise to observe the strength of our approach. Sorry, sometimes I face this. Okay, that is the train data with no augmentation. And now we have the train data with fine grain augmentation in this case. Here we make the fine grain augmentation. And here still some data, even when you make the augmentation, some of them separated, but still this data merge too much to each other. So it is really difficult to understand. So sometimes your data set should not be so easy, but here it seems there are some problems, I say, during the collection of this data set. In this case, you need to remove the problematic one. And then we use that for interference, to observe the sensitivity against interference. Again, we observe this one. Okay. We talk at the beginning of this slide, we talk about the fine grain augmentation. In our previous slide, we talk CDL, TDL, or CDL plus TDL. Why we make them? Why we present? Because they give us some insight on the way to obtain fine grain augmentation. Okay, now you see our final approach, our most recent and most advanced approach for this problem, fine grain augmentation. You see again raw IQ samples, the train test data split, and a splitting train data of different technologies. Here we augment the 5G with CDL, but instead of TDL something, we find the most suitable protocol for Wi-Fi. And when I check some correlation, different mathematical relations, then I see that, okay, TGN protocol, TGN approach is the best one, best transform to transform Wi-Fi data. So I keep Wi-Fi data, and that is the TGN transform Wi-Fi. And that is the CDL transform 5G. And similarly for 4G, I see LTE moving is the best one. So I I augment the 4G data with LTE moving approach. And it is the fine grain augmentation data. Could you see each of these class augmenting different transforms? So here I see, I try to find some low correlated transform with the CDL and also the other with the CDL. Okay, I want the correlation. It is better to find some transform correlated with those one, but not the CDL one. Why we talk about some low correlation with the CDL? Or, for example, the others. Okay, we want to transform this data suitable for those data. But think about, if the LT moving is not suitable for that, it is general one, then it will not have some distinctive effect. Intuitionally, we see that it doesn't make. Think about when you add noise, all of them. What is the difference? Nothing. Even maybe less than 1%. But here, if you make the transform suitable for that data set, still the augmented data seems close to those datasets, but not close to the other datasets. And that is the VGG-based classifier. Again, we use the similar VGG-based classifier. And here the numerical result. Okay, we know without augmentation is this. TDL, CDL plus augmentation is 88. And the fine-grained augmentation. Could you see in the fine-grained augmentation, maybe accuracy on day one is not 99 point, but it is 96.35. And the accuracy on day two, that is more important for us, is 95.61. So it is a very good accuracy when you consider the test with the day two data. Okay, we also give the CDL, TDL, and we talk about the class-specific augmentation, we talk about the TSNA, why we try to visualize, and also we see the accuracy. But let's also observe some confusion metrics. Why we use this confusion metrics? Because we try to observe, instead of just accuracy, it is better to observe that. For example, we have 3 base stations. The base station 1 detected the base station 1 with 94%, but it missed with 6 points to base station 2, and the other is negligible. And base station 2 is detected perfectly. Again, similarly, base station 3 is detected more than 94%, but still it may be misdetect or it is missed in any way. It is detected wrongly as base station 1 as 5.5%. So in this case, we consider the TCNA. In this case, we consider the TCNA training data with no augmentation. We have 3 data: base station 1, base station 2, base station 3, and that is the original data. And after this, we make the train data in this way. Why? Because we apply some kind of fine-grained augmentation, and we change the infrastructure of data. But here, it may be classified better. And that is the test data for that. This test data is simple in some manner. For example, here, it is a bit simple. But here, it is very challenging. For example, to observe this one, especially this challenging. And that is medium challenge. And after talking this approach, we say that 95.6, but we don't put our high score. We even put our lowest score, the least score. Why? Because when you put even 98, the some of our our findings shows 98%, it may be suspicious. So instead of putting the maximum one, even we put the minimum one, not average one, even the minimum one. And the minimum approach shows we achieve still more than 95 accuracy. And after 95 accuracy, what will you do? Okay, it is perfect. In the literature, they achieve 93% something. But, okay, we need to consider sensitivity analysis. We need to consider noise and interference. And here, when you consider noise, that is the input, and that is some kind of noise, and that is the gain, some kind of gain, and that is the output. That is how the noise works. And in this case, we consider base station 1, 2, 3 and their accuracies under each of the following case. First, we consider impact of noise. Okay, if we add the noise on, okay, here in the sensitize, we consider the case with just noise, augmented with just noise, and then we consider the case with interference. We add, in the first case, we add noise on data. In the second case, we consider interference on data, and in third case, we consider both interference and noise. And for each case, we consider 20 dB and 30 dB. When you consider 20 dB and 30 dB, it means that in the 20 dB SNR, signal to noise ratio, it shows the ratio of the signal strength, signal power over noise power. If it is 20 dB, it means the power of signal over noise is about 10. And why we use 20 dB or 30 dB? 30 dB is a better case. Think about that. In the 30 dB, what it means? In the 30 dB, the amplitude of the noise is just 3% of the signal. It is a really negligible one, a perfect channel. When you consider 20 dB, we mean that the amplitude of the noise is 10% of the original signal. Why we say 20 dB? Because in the wireless communication, we have such an assumption. If a channel has a SNR better than 20 dB, it is a good channel. But if it is less than 20 dB, for example, between 13 and 20 dB, then it is a fair channel, and between 13 dB, it is a bad channel. And why I need to train my system with a bad channel or fair channel? So I consider the bound. If it is still good, considered as good in 20 dB, then okay, I need to show the strength of my approach even at 20 dB. But after that, I don't need to do that. If the channel quality is not considered as good, why I need to show the strength of my approach? So we consider the SNR of the 30 dB and 20 dB. And in the first case, we add the noise just for train data. In the second one, we add the noise just test data, not the train data. In the third case, we add the noise for both train and also test data. We augment both sides. And each of case, when you consider all of them, the F1 score, you know, it is some kind of balance ways of precision and recall. It also gives some insight beside the accuracy in the machine learning approach. Then all the scores are more than 90% and mostly more than 95, but just there's such an assumption, such an issue. Here we have 20 dB SNR in both cases, and it is nearly 90% F1 score for base station 1, and the other are still perfect. And the accuracy is here, the accuracy is always more than 92%. Okay, we talk about the noise, and also let's talk about the interference. And in the interference, we need to add some interfering signal. Could you remember the fourth base station? And we use those samples as interfering signal. But we need to take 10% for realizing 20 dB SIR case, signal to interference ratio case, and we need to take just 3% of 3.2% of those interfering signals to realize 30 dB signal to interfering ratio case in the train data. So even in interference, we have some similar result, but some similar approach. Again, the SIR, adding the interference in both sides, make the problem more challenging. And even, could you see, the F1 score for base station 1 may reduce even 77%. But base station F1 score for base station 2 is high, and F1 score is base station 3 is about 80%. So when you consider overall, in overall, still we achieve an accuracy of 86. And when you consider impact of interference and noise, we have here, instead of just considering interference or noise, now we add them. You may say, okay, we talk about 30 dB, 20 dB. Why we obtain this? Okay, if you add, let me say, if you add some 30 dB interference and 30 dB noise, we cannot say it is 30 dB SINR. Let me say honestly, it is about 25. And when you add 20 dB, 20 dB, it becomes 15 dB. So that is why we consider 25 and 15 dB. So SINR means signal to interference plus noise ratio. In this case, again, we achieve some similar result. And again, the 15 dB SINR in both train and test data makes the F1 score for base station 1 reduce 77.5%. And what we did in this one, we used some time domain raw data and 99% accuracy on day one if the classical techniques. Then we use augmentation and fine-grained augmentation techniques. We have CDL, TDL augmentation, fine-grained augmentation, and then we continue with the fine-grained augmentation, and we make 5G CDL, 4G LTE moving, and Wi-Fi WLAN TGN, and we achieve an accuracy of nearly 96% accuracy on day 2 data. And we made the sensitivity analysis. What we can do, we can consider AIS data spoofing and testing our techniques. So these are some references, just that is the kickoff one. So maybe a bit, it is a bit long, some long one. It in the first part is long because we have, let me say, we have 2 journal paper and 3 conference paper, 1 book chapter. So it may be a bit long presentation, but I want to give some motivation how we can consider that for also some AIS data spoofing. So I say that it is better to give more motivation on that. By the way, if you have any question, then I can take the question or answer that, or then I can continue with the second side. What do you think, Professor Sanya? If you have a question, I will be free to, I'd be happy to answer.
We usually practice that you give your talk and afterwards we open the floor for the questions.
Okay.
But I can recommend those who are in that they can just raise a hand if they are interested in something, and we can do it in that way. But my recommendation is maybe for you, Prof, to finish your talk, and then we will open the floor for the questions, if you agree.
Okay, I can continue. Just, you know, it become a bit long. Sometimes people may have directly a question. That is why I ask that. Then I can continue.
Thank you.
Okay. Okay. Thank you very much. Now we talk about the AI ML based approach for IS data spoofing. Okay. In the first approach, in the ground communication, aerial communication, what we made some kind of, especially the supervised approach. When you consider security, anomaly detection is important. Classification is important. Generally, they do the classification with AI ML based classification in the supervised approach. So, when we talk, our colleagues from Maritime, and they talk about that, they say that, okay, they were discussing, okay, we try to deal with some issues, some IS data spoofing. So in that case, we say that, okay, what is the IS? So what are the problems and what we can do? So when I consider this, when I listen and consider this type of problem, I say that, okay, we may apply some, especially AI ML based approach. Okay, there may be some different techniques. They may even consider some techniques by considering some finding some angles, positions, GPS or some other thing to avoid that. But AI ML based approach also can be used this type of IS data spoofing or some other maritime security problems. So I say that, okay, let's continue, let's deep dive on this topic. Okay, we talk about IS. What is the IS? IS is a system used by ships and marine traffic service to exchange the navigation information. So the ships equipped with AIS transponders automatically broadcast the maritime mobile source identity, the position, latitude, okay, the position, where are we, and the speed and course, the vessel name and type and destination data. So it is a kind of identity. You try to give identity, the position, the speed, course. So you give this information, and you say that, okay, that is our plan, that is our position. And what is the ICE spoofing? The sending some ICE message, but false message. A ship claiming to be in different location. So you try to mislead the receiver, right? Or impersonating some other vessels. You try to mislead some others. You try to make some operation, but you may say you are dealing with some problematic issues, or you need to make some problem. You want to make some problem, but instead of taking the responsibility, you try to imitate some other guy. So impersonating some other vessels and creating some ghost ships. They don't exist. This may also cause that. So some people say that, okay, there is for example some ships, they may consider that, but normally there is not such a ship, and this may mislead people. Maybe some people consider, okay, there is such a ship, and because of that, even especially in some war, something, people may make such techniques. You know, even in the classical wars, they try to mislead the enemies. And especially when you consider the military case, some other case, yeah, you can consider the creating some ghost ships that don't exist. The hiding the ship's true identity or location. These are the type of IS data spoofing. But how it can be done? The spoofing transponders, the modify on the IS data, IS hardware or software to send false information, some kind of hacking, or replay attacks, broadcasting previously recorded IS data. So you try to mislead that. The other guy tried to communicate, for example, the original device, original ship tried to send the IS data, but think about, there is a middle guy. The middle guy, that is important when you consider some man in the, it is man in the middle type of attack. in that case, the guy sent the message, but you try to say, okay, everything is fine, but normally that guy's ICE data is not sent to outside. For the outside, the middleman sent some wrong data. So that is the kind of replay attack. And shore-based or satellite scene injection, the feeding false ICE data into networks. Again, it can be done. The purpose of ICE data spoofing, some illicit activities like illegal phishing. So you try to think about that. They don't want you to make phishing, but you are making the phishing. So if they detect you, then it is a problem for you. It is illegal. Then you try to say that, okay, I don't want to give the correct information. I want to mislead the receiver. So maybe you can try to imitate and say that, okay, our ship is just sitting on the coast. It is just standing on the coast, doesn't do anything. But in the reality, it do. So some sanction evasion or some smuggling weapon trafficking or some kind of pricey or terrorism, yeah, again, you can do the IS data spoofing. And the geopolitical reasons, the state actors spoofing to confuse or mislead surveillance. The privacy and commercial secrecy. The ships trying to hide the routes for competitive reasons. So, because of some geopolitical reasons, some state actors can be spoofed to confuse or mislead because of some surveillance issues or the privacy or commercial secrecy. Again, the ships try to hide their routes because of some competitive reasons. This may be done, but I'm not sure for for the last one. Maybe for short one, for the short routes, yeah, you can do, but when you consider the long routes, it is difficult. It may be difficult to hide. The mitigation and detection. When you consider in general manner these mitigation and detection of anomalies in the maritime security, the ICE data correlation can be deal with some data, some radar or satellite imagery or other sensors, or some kind of authentication protocols or regulatory oversight like IMO, I2 enforcement. But also we can consider some AI ML algorithms for anomaly detection. Some AI ML solutions for maritime security. I directly put this figure from a survey because it gives some, I think it is a good figure and gives some insight on that. So I directly take from that survey, and that gives some maritime threats, the marine environment and okay, when you consider marine environment and economic environment, we consider the marine safety, but also we consider the blue economy. Yeah, in the ground they say green economy is something, but we should also consider the blue economy. And for that purpose, what should we do? We should consider pollution. You know, the climate change is one of the harsh, maybe the most challenging problem of the humanity. And also we need to consider accidents for the maritime safety, or smuggling or fishing is also a problem. Terrorist attacks is again. The climate change, we also say the climate considers the air, ground, also the sea, everything. So you should consider all. These are some maritime threats. So think about, even in Turkey we have some mucilage, some other problems. So it will be problematic for people to use their sea, their maritime environment. And when you consider nation security, That is the sea power. But for human security, we should also consider the resilience. These are the maritime threats. What are the suspicious behavior? Some coarse anomalies, like huge returns, tracks with unusual shapes, the zigzag movements, deviate from standard route. This can be some coarse anomalies. Okay, these may be some suspicious behavior. We can say, okay, there are some anomalies. We need to try to detect. If you detect, then you try start to be suspicious. And when you consider the speed anomalies, we have some risky speeds. Think about if the speed is too high, we say, okay, why you need to use high speeds? And some unusual slope. We say that why you are doing such an unusual slope. And the position is the unexpected port arrival or close approach or wrong tag or zone entry. Again, these are the issues. So by using this type of anomaly, by trying to make inference from these anomalies, we try to detect anomalies in the future. So when you consider the supervised ML-based solution for maritime security, we can consider, as I said, speed, features from speed, positions, and course. The speed is risky speeds and unusual stops. For position, unusual positions. Unusual stop, it means the stopping in unusual time. Think about, you are going very fast and you stop suddenly. So you say, okay, what is the problem? Or unusual position. If it is, for example, close to coast, then it is okay. But if it is at the, some kind of middle or nonsense position, we will say, okay, that is unusual position. Or in the course manner, if you make U-turn or drift or spiral movement, then you will say, okay, what's going on? In that case, what you are doing, you will use SVM, support vector machine, or here Markov, or random forest, or LSTM, or even you can use CNN. Depending on the feature, depending on the length of the sample, you may use deep learning type, CNN approach for classification. And these are some accuracy of some supervised learning, like CNN, STM, SVM, HMM, or RF. So here the SVM seems the largest one. If it is simple data, not a large data set, SVM may make better. But if it is really large data set, then we may need more to CNN and LSTM. When you consider when you consider the supervised learning, then in the supervised learning, it is something like that. You try to learn the feature, you try to obtain a model, then you make some interference, and depending on the model, you give some class values, you give some nominal values. For example, you will say, okay, that data, train data is class A, that is class B, that is class B, that is class A, that is class C, class C, class A. That is something like that. Could you see? You give some nominal value. You give some name, some class name to each of those sample. So you supervise the system with the train model. You obtain train model, then you make the test. But in the unsupervised learning, it may be similar, but there is difference between unsupervised and supervised. In the supervised, it is something like that. You are making classification. How you classify that? You already know the class. You have some data and you know their class. One of them is class 1, class 2, class 3, right? You know. But in non-supervised, you don't have any class name. You have some data you don't label them with those class. You say that, okay, I have a data. I don't know how many class or how you will class. Okay, I want, for example, 3 class, 5 class. I'm talking about k-means. Then you say, let's make 3 class, let's make 4 class, and then the data set can be, the data set will be converted to clustered data set. In the supervised learning, we already have class, but in non-supervised, we don't have those class. We let the system to obtain their own cluster, data cluster. So that is the similarity and difference between supervised and unsupervised learning. Again, we have the same parameters. We use this GAN, BN, BBN, CRF, and the other ANN, recurrent network, artificial, DBN, GMM, DBScan1, LSTM, DVC, CEC, something like that. In non-supervised learning, ML-based solution for maritime security. And here in non-supervised, the performance is a bit low, less than the previous one. This is a bit more challenging one. Think about here, we even don't give any direction, any supervision, and just apply the machine learning. And lastly, I want to talk the supervised and unsupervised machine learning based solution for the maritime security. Okay, here you will see some of them are unsupervised learning, the other are supervised learning, and these are the features. That is so. This also shows their difference. When you consider these numbers, I take these numbers, but when you consider these numbers may change depending on the problem. Some data set, in some data set, SVM may be perfect. In some of them, it may be really show very, very bad performance. So it depends on the data set. Depending on data set, you may need to apply ML or deep learning. If the data set is large one, you cannot apply ML. You need to apply deep learning. But if your data set is not so large, then it is better to apply some ML type approach instead of the deep learning based approach. So it doesn't mean deep learning is perfect or ML is perfect or AI is perfect, the other is perfect. Depending on your data, depending on your need, you need to apply some appropriate techniques. So that is my last slide on that. I give here some insight on some approach, machine learning, AI machine learning based approach for maritime security and AIS data spoofing. But here, why I make the first part of the presentation, I consider that, okay, these guys make some anomaly detection based problem, but I think that, okay, instead of that, can we do some type of classification with supervised learning, but maybe not deep learning. Maybe we don't need deep learning. Why? Because when you consider AIS data is, as I remember, is 82 byte. 82 byte means 656 bits. So if you have 656 bit, then it's not a long one. So it may be even it has just less than 700 instance instead of 5 million. So it may be better to apply some machine learning based approach on that. And depending on that, we may apply some fine grain augmentation, normal augmentation, the classification. You can do that. So that is our approach. But if you want to apply that, you need to collect the data. And then one important thing is, okay, we are talking about augmentation. we are trying to obtain some fine-grained augmentation, but we need to understand the data set. Okay, I am giving even the lectures on course on some artificial neural network, but sometimes I say different experience. I talk to topics and so different experience, but what is important? Okay, in the machine learning based approach, you need to deal with your own. You need to try to understand the data set. I haven't put all my result on our fingerprinting, but sometimes even we made some downsampling, upsampling. We try to obtain how much the data is sensitive, something, how the structure is changed. So you need to observe your data set and its performance. And depending on the performance, you can do hyperparameter tuning, something. So I want to, as I said, I talk about RF fingerprinting when we publish many papers. Then I talk the AI ML based application approach on maritime security. Then I want to talk our plan approach to deep dive on AI ML based solution for IS data spoofing. Yeah, that's all on my side. Thank you, Professor Sanya. That is all on my side.
Thank you very much, Professor Gül, for your interesting and insightful presentation. For us from Maritime side, it was in particular interesting this segment that is connected with AIS spoofing, but I think that since in the teams are people who are interested in AI and ML, I think the whole presentation was interesting. And therefore, I will open the floor for the audience. If you have questions, comments, we are welcome.
Yes. Thank you, Ömer, Professor, for the presentation. It's interesting. Maybe two questions. The first one is the second part of this presentation is that this, as understood, this is just a kind of a literature review on the ML-based approaches, supervised and unsupervised approaches. So, have you yourself, your group, have you applied some of these approaches?
In fact, we also discussed with Professor Sanya a few months ago. Normally, we want to apply some of these approach, but we haven't started, deep dive on this problem, iStatus spoofing. So we have some plan. We have some preliminary research, and that is why we share some approach. But even when I share some of these literature review, I say that it depends on the data set. Okay, it depends on the data set, the accuracy is something. So even giving this, introducing this popular approach, I want to note that, okay, depending on your data set, most probably you need to add a second technique. For example, in the first part, what we did, we have some long distance, so we need to apply some CNN, some deep learning techniques, CNN at the core, but it is not sufficient itself. So we made augmentation. And when you consider in the second part, okay, you can do SVM or you can do some other. Maybe you don't need to do do CNN. Maybe applying CNN may cause very bad performance. But in that case, you may, depending on your data set, you may choose one of those techniques. But after choosing those techniques, you may look for some fine-grained augmentation, class-specific augmentation to improve your performance. That is what I want to say. For example, when you have just a few sample of AIS data sample. And if each of them is just 656 bit, then it is not long, right? In that case, it doesn't make sense to apply CNN to that problem. In that case, maybe you may use random forest or some other technique. But I say, most probably applying a single technique will not be as sufficient. This type of problem, this type of AIS data spoofing problem resembles the RF fingerprinting in the classical communication network problem. So I say that this approach maybe resemble, imitate, and adapt to this problem. So that is why I talk in the first part, then I give the second part. Those techniques, there are 5, 6 techniques. It doesn't matter much. Why I say matter much? Because we don't know which data set you will use. For example, okay, we are talking about data set, right? What I say, if you downsample those data set, then the structure of data set may change. Or if you make upsample, the data set structure may change. So you may need to apply some different technique. Or maybe you have 10 sample or 100 sample. So when you consider this type of techniques, the 5, 6, or even let's say 10 technique, machine learning technique, deep learning technique, all of them are not applicable for all problem. Okay, you may apply, but obtain very nonsense result. Very nonsense result, okay. Why? Because they have their own weight. You understand? Some of them are heavyweight, some of them are middleweight, let's say medium weight, some of them lightweight. That is why I say, if you have some long distance, you may apply CNN, but generally when you consider SVM and CNN, SVM generally a simple one, CNN is another harsh one. So today we talk about this AIS data spoofing, but will we consider, when you consider AIS data spoofing, okay, in a problem, if you consider just classical AIS data, it is not long. But maybe in your scenario, not maybe today, but in the future, you may consider some other type of protocol, some other type of information. And maybe some different approach, maybe not just that short message, maybe you will combine with some other message. So in that case, what will you do? You will use another one. But most probably, it will not be, my intuition is, most probably, it will not be sufficient to handle the problem with just one approach, one machine learning based approach. So that is why I say we try to, in general manner, we try to apply some class specific augmentation, fine grained augmentation to empower the strength of your proposed approach. But the important issue about class specific fine grained augmentation is about understanding some, taking some intuition about the data set. I think it is important. Maybe you may need to apply different fine grained augmentation for different scenario. Think about Estonia has Baltic Sea, right? Maybe in the Baltic Sea, you may apply different type of transformation or fine grained augmentation. And maybe because of some other natural issues, if you consider in Turkey, maybe Istanbul, Bosporus, maybe you need to consider, you need to change this type of fine grained augmentation in different way. You understand my point?
Yeah, I understand. Thank you. So the first part was about this RF fingerprinting like technique and this fine graining. So you are planning kind of to. I know there are some works handling anomaly detection in AIS data by checking the RF signal. It's kind of very like this working with the signals. But most of the AIS data, let's say, anomaly detection techniques are handling the numbers, the cost, the speed, the correct position in consecutive messages, etc. So, are you planning to work on the AIS data just from the RF signal perspective, not from the actual, let's say, numbers that they are transmitted in the messages?
I say here we talk about RF fingerprinting, but it doesn't mean we need in the ICE data spoofing you need to deal with the RF signal. You may in the ICE data spoofing, as you see, you consider velocity, you consider course, speed, something. We try to. I say the main issue is try to find some fingerprint. What is the main logic of fingerprint? If you have your unique fingerprint, some kind of unique fingerprint, then you can classify yourself from others. So we try to look for some kind of fingerprint. So that is the approach which can be applied for other type of classification problem. And when you consider this type of anomaly detection problem, that is again the anomaly detection problem is some kind of classification problem. So our approach is some general approach. What I say, in our RF fingerprinting problem, we use CNN, but CNN is not important. You may use CNN. Why? Because data is long. If it is short, you may use another one. But especially the problem is we apply the fine-grained augmentation or something to deal with the challenging part. For example, the guy in the Northeastern, they use another approach. They may say, try to deal with some loss function, blah, blah. But again, it makes the problem complicated, something. But our approach can be applied for different problems. If you consider some other type of classification problem, for example, classifying the dress or classifying let's say animals or something, right? Again, you can consider this type of approach. That is why I say it is applicable. We are not promoting a single method. That is why I say when I present the methods, that is why I didn't emphasize much. They say, for example, okay, one of them is 95%, the other is 90%. Okay, depending on the problem, depending on data set, another one may have higher accuracy. It can change. But
thank you.
Yeah.
Hey, thank you. Do we have further questions?
Thank you very much for the question, by the way.
If you don't have further questions, maybe I will have one. So my question is, in assessing data on, for instance, position of the ship, what is the critical value for you? How do you set or how do you plan to set the critical values for risky position or for risky course or risky speed, but especially position, for instance? How would you set the critical value in data classification?
In fact, it is difficult. I think it is a bit difficult to directly answer for this question when you consider this position. Why? There are two issues. One of them is it may depend on maybe geographical issues. I say, for example, why I'm saying that? It's say, for example, the maneuver. Sometimes they make there is some maneuver or some turn or maybe the angles. For example, if the why I'm saying that? Let me take everything in whole. For example, when you consider some Bosporus or something, some of them are okay, some channels are okay, but when you consider, for example, even the Istanbul Bosporus, it has some different flows and sometimes some different types, and because of that, the ships need to go this way, this way, this way. Of if you go, for example, in straight way, you will hit someone, some place. But if you have for example, straight channel, then your ship may go in direct way, and there is no problem, and maybe traffic is not risky. So in that case, if you say that, okay, the ship is, for example, turning 90% for the 90 degree, 90 Celsius for left, it may be unusual for example, Baltic Sea, but it may be usual for Istanbul Bosporus. Why? Because of geographical issues. That is why I cannot say exactly that one. I think it is more scenario specific, I think. And also, I don't know all the rules, all the results. For example, I say sometimes they may say that okay, you cannot go very close to the coast. In some place they may allow, but in some place they don't allow. For example, in Turkey we have, in the Bosporus we have some special place. I forgot in English name, but we say, let's say Yalı. They are not palace, but you know they are hundreds of $1 million something. So if your ship goes straight, then hundreds of millions and historical houses are gone. We observe such problems, such issues. So that is a problem. But for example, in your case, you may need to consider another one. Maybe because of some agreements, some other issues, you may have some different rules. And maybe because of some neighboring issues, they may have some difference, and they say that, okay, we have 6 mile and you have 12 mile, as I forgot its name, but you say, for example, in Turkey, in agency, they say 6 mile for Turkey, for example, 12 mile for Greece. So in that case, we say that, okay, we need to be careful about the position. But in your, for example, maybe Baltic Sea, you don't have 18 miles, maybe just 3 miles. I forgot the difference. In that case, you cannot apply these issues. So maybe you say that, okay, the position of the ship may be 3 miles close to your country. That is why I say it may depending on the scenarios, I think.
Yeah, a lot of environmental and situational conditions do matter, as far as we understood. So yeah, it should be developed, the model should be developed for a certain environment, and also certain situations should be taken into account. So it's not so easy to, to operate rational, to make it feasible in a level of machine learning. That's understandable.
But the good thing is it is some kind of black box, and on the other hand, when you give this black box, machine learning learn, at least make some interference in some way. So it is the nice one. But on the other hand, as I said, also it may better also need to give some supervision. How we may say, okay, let's classify this data. As I said, in Turkey, we may say, okay, it is normal. But for example, in Estonia, maybe we will say anormal. Or in Estonia, it is normal in Baltic Sea, but in Turkey, we may say, okay, it is not problematic. It is okay. So these are some scenarios. There are some common parts, but also some scenario-based difference, I think.
something that is easy for navigator, especially experienced one, to figure out. It seems difficult for these smart computers. But of course, we have to continue to work in this direction and to keep humans in the loop and to use them, let's say, to learn these machines. And it's back and forward process. Yes, thank you very much for your answer. Do we have more questions, comments? If not, I would like to thank Professor Gül, first of all, for his very comprehensive and detailed presentation and inspiring one. And also to thank you for your patience to be with us in Teams all the time. And with your permission, of course, I will stop recording now.